to the breaking news of this week. The speaker is Ignacio Trujillo. You know him very well because he is member of the seminars committee, actually. And he is giving us the breaking news of two letters that he and his collaborators have published recently. You can see the first authors listed there. Ignacio is one of them, and Javier Cenarro is the other one. And this breaking news is containing both letters. So thank you very much, Ignacio, for this presentation.
Thank you. Thank you all for coming. And also I would like to greetings the rest of the colleagues that is following the talk through the streaming. So today I have used the excuse of this breaking news for giving basically an overview of the topic of the evolution of the most massive galaxies since redshift 2 or something like 10 billion years ago. And so I would present these two letters within this context, but also I would present work that I have been doing in the last 2-3 years in collaboration with several people that include Fernando Buitrago and Chris Concelis in the University of Nottingham, Pablo Pérez González in Madrid, and the rest of the people that is here. So if I were told to give this presentation 5 years ago, probably I would just finish in 2 slides, because 2 years ago, apparently the evolution of these massive galaxies was very clear and very well understood. And the reason was that it looks like a quite consistent scenario, both at the intermediate redshift and at low redshift, telling us that these massive galaxies that today can be well represented by this picture of nearby massive elliptical. These massive galaxies are more massive than 10 to the 11 solar masses. Today, if you take a picture, they are basically 75% ellipticals. They have a stellar population which are all metal-rich. And very interestingly, I think this is a key input that stellar population people have provided us. They have a very short formation time scale. The stellar populations, not only old, but they were formed very, very efficiently in a burst that has taken less than 1 billion years or so. And also they are big objects with sizes of 5 kiloparsecs. So 5 years ago, the picture about the formation of this galaxy, just taking into account the stellar population, would be you take the massive galaxies and they have been formed very early on, at high redshift 3, 5, and since then they have been evolving passively to what we observe today. Also, within the same picture, the studies up to redshift 1, the evolution of the mass function of this galaxy, here you can see the mass functions in redshift 0. This is, okay. From redshift 0 to redshift 0.8 or so. You can see that in the regime, in the most massive regime, more massive than 10 to 11, the number density of these objects were already there. So everything looks consistent that in the last 8 billion years, the objects were there, and the stellar populations were all. So, as I said, this will be the end of the presentation 5 years ago. That can be summarized in the following. So we have the stellar populations coming from, the evidence coming from the stellar population in the present universe and the number density up to redshift 1 suggests that the galaxies were formed very efficiently in a starburst, in a big starburst, in a monolithic-like scenario, so all the gas transformed into a star, and since then it has evolved passively. So this was the picture. So what happened now? So the situation has changed because in the last 5 years we have access to large surveys in the near infrared. So that has allowed us to go to beyond redshift 1 and to explore the properties of these old galaxies in the red frame. And the size of the survey is relevant because we are talking about objects that are very scarce. So the number density of these objects is very low because they are the most massive. And you typically need cubes of, let's say, 20 by 20 by 20 megaparsecs, so cubic, to detect just one. So you need to go from here to Virgo to just detect one of these very massive objects at high redshift. So you need large areas to start finding these objects in big numbers to make statistics. So that was the thing that was limiting the analysis at high redshift. But these studies started, and what we have found is a very surprising result. So again, now let me show you a very massive galaxy of 4 times 10 to the 11 solar masses at redshift 1.8 at the highest resolution that you can explore these objects today. This is an observation with adaptive optics at the Gemini telescope in the K-band. Okay, so we are basically seeing these objects in the J-band rest frame, and with a resolution which is 3 times better than NIGMO. So this is the best high-resolution image that you can see of these compact objects. So look at that the size is 1 arcsecond here, but more importantly, this is the size in kiloparsecs, and then you see the surprising result that the object is contained in really a small fraction of the... so you see that this is 5 kiloparsec, and you have basically the object full contained in 5 kiloparsec. Remember that the previous object that I showed you in the local universe, the effective radius, so half of the light, was 5 kiloparsecs. Here, the effective radius is 1 kiloparsec. And you can see this much better in this transparency. So this is the size, and this is the stellar mass, okay? And this is the local relation of these galaxies, taken from the Sloan. And the points are the work that we did 2 years ago, exploring with the Palomar survey, with data from the HST. And you can see that as soon as you move in redshift, this is redshift 0.3, 0.7, 1, 1.2, 1.6, 1.8, you can see that the distribution of points is going down and down and down, implying that at the given stellar mass, an object, let's say 10 to the 11 solar masses in the local universe, as we said before, have 5 kiloparsecs in effective radius. At redshift 1.8, it have only 1 kiloparsec. So, well, this evolution is enormous. So this implies, if you think on the density that these objects have is, the mean density is 2 times 10 to the 10 solar masses kiloparsec cubed. So if you want to take a look to a nearby object with the same density, you have to go to a globular cluster. So the density of the most massive galaxy high redshift is enormous. In fact, here I have quantified the same result than before, but extrapolating, well, including data up to redshift 3 from Fernando Buitrago. And you can, so if we concentrate on the spheroid objects, you can see that this is the local relation, which is 1. So at redshift 2, we have that the objects were a factor of 5 more compact. Now, there are several observational issues that you should control. For example, you can tell me, maybe you are missing the light in the outer region where you are identifying wrongly the size of the object. No, this is a possibility. The other possibility is that you have K corrections, so maybe you are only observing the ultraviolet at high redshift. All these things have been systematically studied in the last papers. And we can, particularly, we would like to show you one of the latest one from another group, which shows the typical stellar mass density profile from one of these high redshift compact galaxies compared to one in the nearby. So this is the size in kiloparsec, this is stellar density, and you can see that the observations at high redshift are deep enough now to tell us that what we are really observing is an absence of matter in the outer region. So it's really the object is compact. Okay. So I think the situation now is that these results that has been studied for more than 3-4 different groups, and there has been like 10 or 15 papers on this, is that this is a reality. So the most massive galaxies at high redshift are much, much more compact, almost a factor of. Yeah, the masses have estimated through the filters, through different filters, 7-10 filters, and also I would expand on this later on. Okay. In which sense? Because these objects are the most easy one of detecting in terms, because they are the brightest. Okay, so we detect up to 10 or 100 times objects more fainter at that redshift. So these are the most easy. I mean, if we are making something wrong, these are the ones where you can be much more confident because these are the brightest objects.
Yeah, but you have to keep in mind the signal noise up to the measure the distance.
Yeah, this is the meaning. This is a factor of 2 sigma. Yes. So exactly. I have not space and time for putting all the figures, relevant figures here. But we have made the comparison between the NIGMOS data and the ACS data, and the sizes are the same. So even moving from ultraviolet res frame to optical res frame, the sizes are equivalent. So the objects look. We have, all the details, all the numbers that you see here, the res frame, the size has been identified in the res frame B band, okay? And it has been taken into account these K corrections to do not mix this effect. Now, so let me summarize the situation. So we have star formation, time scale, and all metal-rich stellar populations in the nearby universe. We have a moderate or very low number density evolutions in redshift 1, and we have, however, we observe 3 milli size evolutions in redshift 3. With all this data, there has been several theoretical ideas to explain how these extremely compact massive objects have been transformed into what we see today. Because you don't have too much freedom. You cannot modify too much the stellar populations because you have the constraints on the local universe. On the other hand, the number density looks very similar, so you cannot play too much with the mergers and things like that. And also you have to search for a mechanism that has to be extremely efficient on increasing the size of the objects and at the same time not increasing too much the mass. So you have several constraints. The number of ideas that has been suggested is limited, but can be summarized in these two ones. So one is the puffing up scenario. So we know that at redshift 2, redshift 3, the AGN activity was enormous. So the idea is that we have a lot of gas in the galaxy. The galaxy has created all the... So imagine that you have a very efficient collapse of the gas, and you have transformed efficiently this gas into stars, so you have your object, but then you have still quite a lot of gas. Now start the activity of the black hole, the AGN, and remove all this gas very efficiently, and then what happens? You have modified the potential depth very quickly, so the galaxy expands naturally. No, it's something similar to what happens with the globular clusters also. So you create them in a much more compact region. On the other hand, the other possibility that you have is that we live in a hierarchical universe, so the gravity is always there, so we are merging objects continuously. But the mergers that have to be of use for this kind of galaxy have to be what it's so-called dry merger. What does it mean? That when you merge two galaxies, you don't create more new stars. Okay? So it have to be only just an aggregation of stars. Because if you create more stars, you increase the mass more efficiently, and then also, when you have a lot of gas, you have dissipation, and the increasing size is not very efficient. So you need something that has to be dry, okay? Dissipation less. So these are the two ideas. And now came what we, as a group, have been working in the last years. Doesn't play a role because the objects are disconnected gravitationally from that expansion. So this is only valid for objects that are not, in a Hubble flow or whatever. Okay. But once you have collapse, you are in a different metric than the Hubble expansion. Okay. So here, these are the questions that we have addressed in the last 2-3 years. Particularly, the last two ones is the one that I will present as breaking news. But I would like also to show the result that we got last year in relation to the star formation history of this galaxy. Because as I have been telling you, the evidence from the local universe is that these objects are all and have been evolving passively. But this is something that you really would like to test also. And we can have now access to incredibly good data, high redshift, so we can explore whether that star formation histories are real, so passive as people is telling or not. So, and this is what we did here in last year, the work that I did with Pablo. So here, there are two pictures of normal elliptical galaxies at redshift around 0.7 and the other one at redshift 1.7. So you can see how they look in the ACS data. But what is new here is that we add another filter, the 24 micron, okay, here. Okay, so this is the spectral distribution of the object up to 10 microns, and then we add another point at 24 microns. So why is this relevant at all? So people that have been taking a look to this elliptical galaxy, high redshift, have been claiming that these objects were passively, and all the information were basically coming from this region of the spectral energy distribution, the optical rest frame region, okay, the optical near-infrared rest frame region. And in fact, it looks like a normal spectra of an elliptical galaxy. So people would say, just based on that information, that the objects were passive. But if you add now the information on the infrared rest frame, this is around 20 micron, 15 micron, in this region is where you have the emission from the cold dust, okay? From the hot dust, sorry. And you can, I mean, the expectation would be that if there were no emission, the object would be like this. But if you have hidden star formation by the dust of this galaxy, you would see the emission caused by the dust. So we have explored systematically what is going on with this galaxy. And here is the result. So this is for all the spheroid galaxies, and we find 3 different types of spectral energy distribution. For around 40% of the objects, in fact, we find look at this, this is the elliptical spectral energy distribution. You will expect that these objects go down. So we found that for 40% of the objects, even using the most deepest, the deepest observation with the pixel in 24 micron, we were unable to detect a measurement. So these are upper limits, okay? So this is in principle compatible with not being star forming at that redshift. But the surprise came that another 50% of the objects were detected in the infrared both at 24 and at 70 micron. And you can see that these objects that look in the ACS data as a normal elliptical have a spectral distribution which is more common to a spiral galaxy, a late-type spiral galaxy today, okay? Even that they look morphologically like an elliptical. And you can see that before, all people working in this regime would be unable to identify this galaxy as an active star formation galaxy, because you can see that up to 4 micron rest frame, they look, both spectral distribution looks very, very similar, okay? And then we found a contamination of 10% of the spectral distribution that look like AGN. So what are the conclusions from here? So what we have found is that so let's concentrate on those galaxies that we are able to detect the emission from the dust at high redshift, no? Which are 50% of the spheroid galaxy. So this is a panel showing the specific star formation rate versus the redshift. So, and these crosses, the red crosses, show the evolution of this quantity for the spheroid galaxies and this for the spiral galaxy. So it's a very busy plot, but let me explain you what we find. So at redshift 2, or redshift beyond 1.5, you can see that both the spheroid galaxies and the spiral galaxies are forming stars very, very efficiently. So this is around 100 solar masses a year. But as soon as the time goes, okay, as soon as we move below redshift 1, both components start to separate. So this is for 50% of the spheroid galaxies at high redshift. So what this is telling us is that this idea that this object that look spheroid has been evolving passively and quiet is not so true, at least at the very high redshift. So yes.
Picture that you present at the beginning with the monolithic evolution tells that everything was formed at c equal 2. So actually,
there is a
the fact that you find a lot of star formation even in this object at c equals 2 is very consistent with the previous picture that you have been describing.
Yes,
right?
but what I want to say is that this is right, but it would be right for these objects if they just simply switch off there and evolve passively. But what we have seen is that the general population is evolving smoothly. Okay? It is true that maybe this amount of star formation, this is around 10 solar masses a year, redshift 1, with the spectra that we have right now in the local universe, we are unable to distinguish this from just simply something that was very efficient at high redshift. But the point that I want to make is that the galaxies, this picture is not consistent, at least for 50% of the elliptical galaxies, okay, that we have been following in redshift 2 to now. that they were just formed very efficiently and then switch off and nothing had happened. So it seems that for whatever reason, maybe new infall of gas or whatever, the formation in the elliptical galaxy has been continuously, although decreasing very, very quickly, no, in the last 8 billion years.
And I have another question. It's concerning your previous view. Is it easy to explain why, if you detect emission in the infrared, this means star formation? Why you cannot have just hot dust?
From the AGN, for example.
Or that has been hot for a while. I mean, you switch off the star formation and the dust remains hot for a while. And this, I mean, the time scales at C equals 2 are very short. So you might have something that heats up the dust, and it takes a while to relax, to cool down. And so
I have no idea of the time scale that can go from star formation, hit the dust, and then the dust cool down, and you don't see the mist.
So it might happen that, of course, you have star formation at C equals 2, and the dust remains heated for.
But I don't. I think the time scale would be really short. But I'm not an expert, so maybe.
What do you mean by a long while? Because the time scales at C equals 2 are very, very short.
Yeah, but I mean, between redshift 1 and 2 is 2 billion years or so. I think so. We are talking about 100 mega years. So.
What is the time scale?
No.
What is very quickly? A million years? 100 million years? Because the age of the universe at that time was very, very short.
Yeah, it was short, but not extremely short. I mean, this is 10 billion years ago, redshift 2, and this is 7 billion years ago. So we have like 2 or 3 billion years in between.
Due to stars. That is why, because it's very fast, exactly. But I mean, you see this type of data associated with AGN is the lifetime of AGN could be 10 to the 7 years. That's it. But to have that dust heated by a star.
Look, this is the spectral distribution of an elliptical galaxy, so no star formation today. Okay, a spiral galaxy today, late type, and an AGN. So you expect that the AGN emission is much more higher than what you typically measure. Okay. So it looks like more related to star formation than to another source of heating of the.
Jorge.
This is 10 to 11 old, or a little bit more. Okay, but this is selected for being very massive. So and then so once we have studied this, the natural question then is there any connection between being star forming and the size of the objects at a given mass? Okay, because this is one of the things that we would like to test on this evolutionary scenario. And what we see here is that, again, this is the panel of size versus stellar mass, and this is the local reference, as always, redshift 0.3, 0.6, and so on. Red stars are those objects that are detected in 24 microns, and the open symbols are those that are not detected. Not detected doesn't mean that they don't have star formation, but we are unable to go that limit. No? And you can see that there's no at all clear difference between being clearly star forming and maybe being not. Okay, so how this connect to the two theoretical scenarios that we have been discussing? Well, so this is a summary of this paper. So more than 50% of the massive spheroid-like objects are star forming at all redshift. The star formations declines very quickly for these objects, and the star formation and size are unrelated. So sadly, the prediction from the two scenarios are not can both accommodate, if you want, a little bit within this idea, because you can have the objects that are being created now, then the AGN activate the removing of the gas, so the star formation goes down. So you can always have a play, and the pathing up scenario is unable to say whether this is incorrect or not. And the same is also for the mergers, because you can have the mergers can infall gas to the galaxy, and then you can activate. So it's not clear. Okay, so that's why we went to another test, which is the first letter, the first breaking news. Now, the question is, so it would be fantastic if you think twice on this in the following. So this object that has been very compact at high redshift, if I were just able to find one in the local universe that has not been suffered any merger or this activity, I would be finding objects that are relics of the high redshift galaxy, of the early universe. So I can go to these really compact galaxies today, and then I can take a very high signal-to-noise spectra and identify properties like how were the metallicity, the stellar population histories, or all kind of detail of the high redshift universe if they were just simply not evolved since then. And in fact, this was the prediction of early models. So they say if the merger scenario is right, there will be a fraction as big sometimes as 10% of the object that could have not suffered any merger, and they can survive in redshift 2, for example, to now without, in complete isolation, without any suffering any contamination from other galaxies. So what do we have to search? So this is redshift between 2 and 3 from the Fernando Buitrago results, and you can see that the typical sizes at the given stellar mass of 10 to the 11 or so was around 1 kiloparsecs. So it was obvious then to go and to the Sloan data and to search for any very massive galaxy that is more compact in effective radio than 1.5 kiloparsec. And this is what we did. So we decide, so this is the size versus stellar mass for the nearby galaxy population, okay? And this is the local distribution. So you can see that at 10 to the 11 solar masses, you will expect to find objects of 5 kiloparsecs. The same story that I have been always saying. Now, let's select only the galaxies that are within this square, okay? Which are objects that are very massive but very compact, and take a detailed look to how they look like, the spectral energy distribution, and morphologies and things, because it will be a fantastic window to the early universe. So what do we found here? We found around 200 objects, but 150 of them were quasars. And this is what expectations somehow, because they look compact because they were just emitting like a star. But there were a remaining... This is mass in units of 10 to the 10. This is 10 to the 11. 10 to the 11 solar masses. So we select from 8 times 10 to the 10 solar masses. So we found this tiny fraction of galaxy, which are around 50 objects, which correspond to less than 0.03% of the total population today. So if there was, basically nothing survives in redshift 2 with that properties of being massive and compact. So whatever mechanism was very efficiently on growing the size of this object, okay? So what are the characteristics of this object? So this is how they look like at very bad resolution. This is the resolution of Sloan. This is 1 arcsecond. So you can see 1 arcsecond the PSF. This is so you can see that you basically can say anything. They could be elliptical, they could be phase-on spiral, they could be anything. We have tried high-resolution imaging with the Space Telescope. We were not successful. We will try it again. And also we asked now to the CAT for adaptive optic. We put a proposal for making an adaptive optic of these objects, which are very bright, magnitude 17 or so in our, and very close to a star in some cases. So we could try to make a high-resolution view, which would be fundamental to distinguish whether these are elliptic, which morphology they have, the compact objects today. But we had this enormous surprise when we studied the spectral distributions given from Sloan. So as I told you, let me go back for a second. So we select a sample of objects here. We took the spectra to take a look to how they look like in the Sloan, to compare this with the spectra of the objects that are in the compact region. And this is what we found. So the red one is the spectra of the galaxies that are normal in size at that 10 to 11 solar masses. And the blue is the typical spectra of a compact galaxy of 10 to 11 solar masses. And you can see immediately from the spectra that the local compact galaxies are younger. So you can see that in the blue, they are more brighter than the normal population of elliptical galaxies. So we can do now an index diagram to understand better the metallicity and the ages of this galaxy. And in fact, we found that this sample of compact galaxies have a typical age of 2 billion years compared to the typical 12 billion years or whatever number, very old, for these massive normal elliptical galaxies today. The metallicity is much more dubious because we have an error bar here that is not so clear, but it looks like these were a little bit more metal-rich than the normal galaxies. So, what are we seeing? So we would expect that these objects were relics from the early universe, and maybe only 0.03% of these objects were survived. And however, when we analyze the star formation history, we find that these are very massive but very young galaxies. So we have speculated that maybe what we are seeing is the last tail of the formation of the most massive galaxies. So the formation of the most massive galaxy was very efficient at redshift 2, 3, but you have formation of very massive galaxies at all redshift. And maybe now we are observing just the final end of the formation of the most massive galaxies that we have in the local universe. So in any case, as you can see, whatever the interpretation of this, it would be interesting to have even higher signal-to-noise spectra and high-resolution imaging of these galaxies to see whether we are catching the formation of these massive galaxies in high detail and resolution today. No? Could be. And in fact,
They are less dusty, more dusty than normal.
we have a detailed analysis in progress. Also, we have got time for much higher signal-to-noise spectra, and it would be very nice to have access to the near-infrared. Yeah. So the indices, you are more expert than me, no? But so there are also evidence of different depth on different lines and things like that. That it goes in the same direction that these are really younger, more than dust.
And why you don't see supermassive stars also?
Supermassive stars?
Yeah, I mean, at this age, you will expect 100 solar masses stars with superbubbles, so you will expect to see a lot of gas and H-alpha lines. And
yeah, well, you can see that here the object is compatible
I don't
with...
see any emission line.
No, in fact...
So for me, this is very weird that it's a 2 giga-year galaxy.
2 billion years, so all the emission has gone.
In 2 giga-years?
Quick question is about the stellar velocity dispersions.
We go there. This is the second letter. Now, summary of these results. So, very few objects, very massive and compact today, compared to what it was the common nature of this object high redshift. These objects are young, and they are not relics from the early universe. So, this doesn't fit well with some scenarios of with some hierarchical scenarios that they were predicting a more larger number. We will go then again to that. But also, it's not in agreement with this puffing up scenario. In which sense? So apparently, they look like they are in agreement because they have all this old population disappear, and that's why we are not observing any compact galaxy today. But the prediction from this puffing up scenario was that something as soon as 1 billion years, 2 billion years, the galaxy would be as big as the object that we have today. We are finding objects that are young, that are still compact. Okay? So young, I mean intermediate age, 2 billion years. So in principle, more than enough time for being bigger. No? However, we are not finding that. But now I come to the point. So everything, most of you are putting weird faces. So now the key thing from all these studies is to measure the central velocity dispersion. This is key for several reasons. First, do we trust the masses at high redshift? So we need some independent measurement, and one kinematical will be key for understanding this. Okay? And also, for these compact objects, no, your question was, what is the typical central velocity dispersion? It's 200 few. Okay, so they are massive. So. No, but what I want to say is that for understanding IMF, initial mass function evolution, for trusting definitely these results or not, we need a measurement of the central velocity dispersion. So a measurement of the mass that is not related to any filter or whatever, luminosities or whatever. So this is what we have done. So what are the predictions? The predictions are So if you were able to measure sigma of this galaxy had high redshift, so the stellar mass would be basically the same, so this will be not changed, but the effective radius is a factor, let's say 4, a redshift 2, smaller than today. So you put these numbers into the equation, and you will expect to measure central velocity dispersion of a factor 2 times higher. That means central velocity dispersion of 400 kilometers a second. This is the naive expectation. If the galaxies were just a pure homologous system, that you just simply make it more compact at high rates. Now, if you think this is the naive expectation, now you think twice on this. When you say, wow, 400 kilometers a second, how can I make this object to expand at all? So it's huge. The potential depth is huge. So, you know, there is some tensions here, even if the objects were just simply evolving like that. Now, the models are very clear on the predictions here. So in the puffing up, so in the aging activity, this will be the expectation. So you just remove the gas, you expand the object. The central velocity dispersion will be 400 kilometers a second at high redshift. The mergers, however, tells you that the evolution will be really, really small. Why? Because most of the activity of the mergers of these objects, the predictions are that they go to the outer region of the galaxy. So they basically doesn't touch the inner region, but just simply put matter on the outer regions, making the size grow very efficiently because they put more mass outside. No? So let's go and study this. But this, you know, this is extremely difficult and extremely in capital letters. The reason is that beyond redshift 1, you have moved all your stellar models and things like that. You need to go to the near infrared. And if you go to the near infrared, you have all kind of travels with observationally, okay? So you will really need to go to the space to make this analysis quickly and efficiently. So if you want to do this analysis, from the observational point of view, people have concentrated on the optical spectra. But in the optical, beyond redshift 1, as I've been commenting, you are in the ultraviolet red frame. And if you are in the ultraviolet red frame, the problem that people was facing is that they don't have high enough models to attack the problem and measure in sigma. In addition, you need to make such a crazy expositions on time exposition on the galaxies that at some point is prohibitive. So this spectra that is here was the only thing that we have available. This was publicly released by the group of Cimati and collaborators. This is the black line, sorry for the other ones. And this is the average spectra of 480 hours. So they took these 13 galaxies, an average of the order of 40 hours in each galaxy, and then they put all together to produce a single spectra at redshift 1.c taken with the VLT of 480 hours. Okay? And even though the signal to noise is not fantastic, as I will show, but because we didn't know that it was impossible, we did it, no? and we tried to measure the central velocity dispersion of this spectrum. So we cut the spectra in different pieces, and we use different templates. For example, in this range of between 2,500 and 3,000 Armstrong, we apply this CoolCat stars library that from the Hubble Space Archive, and we try and we use the different models and so on, and we put it into we try to make a fit. And basically, because this was a very nice feature here around of 2,800, the magnesium feature, and also of the goodness of the fit, we get a value of 260 kilometers a second, plus minus 20, plus minus 100 or 50, whatever you like. But 250, it's not 400. This is the point. The very important point is that it's not 400. But how accurate can be this? Now we change the template. We now went to the new releases of models from Brusol and Charlotte, the same range, okay, another fit, but it was a good fit also, and we got 240 plus minus 20. Again, not 400. The same region, different templates, very similar values within the errors. But now we went to another spectral range with a different template. So this is more optical, 3,000 200 to 3,900, using stars at higher resolution from the Keck library, and we get another good fit with another 266 plus minus 15 kilometers. So different regions, different templates provide a very similar value. Okay? So, of course, we know that this has several issues here. We are combining a spectrum, so you have an internal accuracy on the error. Also, not all the galaxies that were shown there are spheroid. There was some contamination of spiral that could be diminish the value of the spectrum. But we think that taking into account all the details, no, we can confidently claim that this is not such a bad value. It's more or less representative. And in addition, if you are still uncomfortable because it's a combination, what we can say is that all the effects that you can consider are going to make this an upper limit, but never a lower limit, okay? Because of the problem of combining spectra and things like that. So I think the massive objects at redshift 1.6 have not a high central velocity dispersion. So the next thing was to put this within context, and this is what we did here. So this was the very first time that these two evolutions were shown together. So this is redshift, okay, from redshift 0 to 2, and this is the effective radii and the central velocity dispersion. So this is the data that we take from Sloan, data that we took from a compilation of data in the literature, and the new point that we put here. So this was the result from previous studies. So this is not a fit, this line here. Okay? And you can see that the objects that we were selecting were representative at all redshift of the typical size. So we are confident that these objects are not weird things. So we see the typical size evolution that we were saying for objects of a given stellar mass, this factor of 4 that we were saying. And now look at the evolution of the central velocity dispersion. So these are all based on individual spectra, so not the stack spectra at all. And this is the new point that we have put new with this stack spectra at redshift 1.6. And this is the prediction from the scenario of the AGN activity, so the pathing up scenario. And this is the prediction from the mergers activity. So even if you don't trust this point, for whatever reason, you can see that at redshift 1, there was clear evidence that the galaxies were not evolving, the velocity dispersion was not evolving just naively as one was expecting from the AGN activity. So something has been dominating the evolution of this massive galaxy. So if you want to understand this in a little bit more detail, what is going on, apart from what I say that most of the activity of the merging is going to the outer regions according to the models, and consequently the evolution in the central velocity dispersion is small, just a very easy interpretation of what is going on also there is that once when you measure the central velocity dispersion of a galaxy, you have two components that is producing this central velocity dispersion. One is the baryonic matter, and the other one is the dark matter. Okay? So what happened? At high redshift, the object was very concentrated. Okay? So the central velocity dispersion was only dominated by the baryonic matter, basically. But if the baryonic matter has increased for whatever reason, has expanded, now today we have a contribution both from the dark matter and the baryonic matter. So in fact, the fact that the evolution in the central velocity dispersion has not been enormous is because the dark matter halo is somehow avoiding such a huge evolution, which is in fact what happened in this AGN activity scenario, where they have not, this was not very well taken into account, and consequently everything was dominated by the matter on the baryonic case. Okay, so just to summarize, these are the summary of what we are finding. So there is a weak evolution of the velocity dispersion in redshift 1.6. This has important consequence for the IMF. In which sense? The initial mass function. So several people was claiming that the fact that we are observing such enormous evolution in the size was based that we were measuring very, very wrongly the mass. But what we are coming here is with the number that, look, the IMF could change with redshift, it's natural, consider that. But take into account that an object of 10 to 11 solar masses obtained from the spectral distribution has a central velocity dispersion which is of the order of 240 kilometers per second, so it's very massive. So you cannot have a very strong evolution on the IMF. So the results are robust, I will say. And finally, I would like to finish the talk with open questions, which I think are the interesting point here. So if the AGN activity, for several reasons, is unable to explain the evolution of the most massive galaxy, and on the other hand, the mergers, at least the major ones, the one-to-one, doesn't look like a good mechanism, because when people like Carlos or whatever has studied the merger fraction, they have discovered that the evolution of the merger is very low, of this massive of this one-to-one merger, so the very massive galaxies combining with very massive galaxies. So we have a very few alternatives, and one is this minor merging. No? In the last 3-4 months, the community have turned off the attention to this channel as the way of increasing the size of these galaxies. So the theoretical expectation, and this is something that we can go and test immediately if we have the data, is that the number of satellites of these very massive galaxies at redshift 1 would be much higher. And that's why they have been accreted to the massive galaxy and have created this long tail. Okay? But this is something that it have to be done. And you know, those that are willing to do it can do it. So I will finish here. Thank you.
So there's time for a few questions.
Nacho, what are the sigmas of the compact objects at low redshift, the ones you found with 2?
It's around 200 few, also 220, something like that.
Yeah, just a comment about dry merging. You mentioned dry merging may code for accretion, but also for the opposite, because dry mergers also take out mass from the galaxy, and you have different variables. And one of the key points is the dark matter. Well, we have a paper of dry merging without dark matter, and another coming soon. I can show you, and this is an important point, because dry mergers we claim are the most important contributor to the intergalactic mass. So it is a question of masses. So you may have accretion, but you also are losing mass. So it's not a
the loss of
model.
Yeah, but losing mass would be only very, very efficient if you don't have dark matter, because otherwise the dark matter halo will.
And also depends on the mass. I mean, when you have massive elliptical galaxies, you may lose up to 10% of the mass of the galaxy through dark mergings.
Yeah, but it's a small number anyway.
Is the presence of dust not a worry if you look at these UV-determined velocity dispersions? Because I can imagine if you look in the ultraviolet, all you would see is sort of the outer shell, the nearby outer shell of the galaxy. So if you get a 240 kilometers per second dispersion from that, then if you wouldn't have the dust and you would see the whole galaxy, you might easily get to 400, I think.
Javier?
So can you repeat?
I'm worried if you look in the UV at your velocity dispersion, that you will just see the top shell of your galaxy. You won't be able to look into your galaxy. So the velocity dispersion you measure is just going to come from the stars that are nearest to you in the galaxy. You know, because light from further in the galaxy won't reach you at all. So if that gives you 240 kilometers per second, then the whole galaxy integrated might easily get a much higher value.
But correct me if I'm wrong, but the velocity dispersion, at least in the elliptical galaxies today, okay, are very homogeneous and stable. So you do not expect this huge. So we do expect sigma 240 outside. So you will expect something very constant.
You will expect a much younger population itself in these galaxies. I mean, you don't expect so much extinction. You will expect much younger SSPs, and what you observe is typically, for instance, in this paper by Cimati, the spectra of this stacked. I mean, this stacked spectrum was determined to be like 1 gigayear or so. So we are not dealing with really young objects in which these effects can be so important. I think.
Can I ask a related question? If you do this in local galaxies, determine the velocity dispersion in the UV, do you get the same measure as you use the optical?
I don't know.
I think that's the key.
Detectors are not efficient in the UV. You don't get signal.
To do, and even from all the archives, I mean, even from IUE, you have average so many spectra, you can get an IUE spectra and do it. Yes, data there is to do that, definitely. But there is something. Sorry, I think I don't understand. If the velocity dispersion is about the average value, I mean, nothing is special. But then, according to this relation with the mass is lower by a factor also too.
No, this object, I mean, the evolution.
Why?
No.
If I put the number in the formula back, my mass is.
No, because look at this. We selected the objects to be all around 10 to 11 solar masses, okay? So we remove this factor from the. So this is not selecting very massive, more massive galaxies at redshift 2.
How are you determining that mass?
That was determined from the spectral distribution through the filters.
But maybe that is wrong.
Yeah, but that's the point. So if we were really wrong, maybe the central velocity dispersion were very, very different.
But maybe the velocity dispersion is right. It's the mass that is wrong.
But I think this is a consistency test. So a consistency test. So the velocity dispersion have not changed too much at a given stellar mass.
Yeah, but it may not be at a given stellar mass.
Absolutely, absolutely. You can always have. This is an uncertainty, but I think it's a test that you should try anyway. No? There is another proof that you are not making the IMF very wrongly. But this will take me quite a lot to expand on this. No? But one thing, just very quickly, is that if we are measuring, so one thing is that, so let me go back for a second. So imagine that we are measuring the mass very wrongly. Okay? So we claim to have an object of 10 to the, let's say here, 2 times 10 to the 11 solar masses at high redshift, okay? But we are measuring the mass wrong by a factor of 20, because this is the amount of evolution you need to put these objects in the local relation today, okay? So if we are doing this wrong by a factor of 20, we have a problem. And the problem is that here, the most massive objects look compact, but the studies that we have been doing for objects with this mass shows that they are basically not evolved in size. Okay, so the evolution is only here. Okay, for this mass range, not here. But if I'm making a mistake on estimating the mass here, probably I'm also doing the same mistake here because it's based on the same techniques. And also here, the error bars are much larger because these are the most brightest objects. So that will imply that if I'm doing very wrongly here, that the objects that I'm seeing here will locate it much more farther away, and that will imply that the objects have decreased in size in redshift 2 compared to what we observe, okay? Because you put the objects above the local relation. So I think this is a good reason for trusting that the masses are not very wrongly. Another possibility is that you say that the AMF for the most massive galaxies are different, but then you are assuming that the objects are different in mass. So you see that it's not easy to understand that you are doing very wrongly the things there once you have measured the central velocity dispersion.
My question regarding velocity dispersion was redshift 0, for example.
Yes.
How does compare the velocity dispersion?
The compact, yes. Yeah, for example, in the control sample, this is around 180, 190 kilometers a second. Here is 210, 220. So these objects are more, the central velocity dispersion is a little bit higher here.
Okay. Could you put this formula to compute, I mean, the dependence of the velocity dispersion on the masses and scales? Maybe you mentioned this, but I lost it. the effective radius, this increases from z equals 2 to now by a factor of 4. Now, could it be that the masses increase also by this amount, but not the baryonic mass?
But the dark matter.
The dark matter. I mean, that the galaxies are creating.
Absolutely. This is something what I was trying to say also. So this mass is the contribution from two masses, the baryonic plus the dark matter. Okay? So in fact, if the naive expectation were not working, okay, if you don't see, so we have saying, just assume that the only thing that changes is the effective radii. Then you will expect the central velocity increased by a factor of 2. Now we know that these two are very similar. We also control this effective radius, so we only have as freedom the mass. But we have fixed one of the two contributions of the mass. The baryonic mass is fixed to 10 to the 11. So the only possibility is to change the dark matter contribution. And this is what I have been telling before. So a high redshift, the dark matter contribution was, if you put all this into this equation, what you get is that at high redshift, the dark matter contribution to the central velocity dispersion was much more smaller than today.
Yeah.
So
an accretion of dark matter would explain the expansion of the galaxy too?
The accretion of dark matter, I don't know for sure, but take into account that dark matter accretion is non-dissipative. Okay? So in principle, you are not going to. So this is a property of the very central region of the galaxy, or the central, including dark matter. I mean, so if you have accretion of dark matter, the dark matter will try to accommodate on the central on the potential halo of the dark matter, but mostly again in the outer region. Okay, so what do you expect is that the central velocity dispersion will not change because basically you don't have dark matter. The dark matter is not dissipative and doesn't go to the center, doesn't modify the properties of the center of the galaxy.
Nacho, in your nearby universe compact sample, you don't really resolve the effective radii, don't you? I mean, they're like 0.16, so you
let me remember.
Effective radii, like.
No, we resolve it because effective radius will be of the order of 3-4 seconds. But I'm talking using my bad memory, so.
Yeah, 0.18.
So look, this is huge. This is huge. 26. So, and the PSF 1 arc-second, and I think if I don't remember wrong, that the effective radius was of the order of 3 arc-seconds. So you resolve the.
You don't expect them to be even more compact?
No. I think we are at the limit. We test this with different with different tools, using also GALFIT and also the data that they were given from the New York Value catalog and so on.
After this very interesting and lively talk, I encourage you to give talks of this kind after your papers are published or accepted for publications. Just if you want to do that, contact any member of the seminars committee or send an email to seminarios@iac.es, and we can organize the seminar on the date that is more convenient for you. So let's thank. Okay.
Yeah, I would like also to say that I will be here the rest of the week and the week later and so on.
So let's thank the speaker again.